Okay, so now the webinar is going to be live streamed. All right, so I'm back to the meeting now. So Sohan, you can take care of the questions which are being asked by some students in the background, if you can handle them.
Okay. Yes, I'm working on that.
Yeah, so friends, this is just a revision that the shape that we have chosen is a modified GNVR shape in which the front elliptic portion, the rear circular and parabolic portions are matching with the GNVR shape, but we are introducing a cylindrical portion to increase its length, and we use the cylindrical portion to be A times the maximum diameter. Now, the length over diameter ratio will be 3.05 plus A upon D max, because for the basic GNVR shape, the L by D is 3.05, and hence if we use A equal to 1.2, that means if you use the cylindrical portion equal to 1.2 times the max diameter, you get an L by D equal to 4, which is what Sohan mentioned he requires. I would request you to take a picture of this particular slide because you might need it for the calculations. Even if you don't take the picture, the formula will be shown to you once again. Okay, so the envelope volume will be calculated using the simple formula pi by 4 into A, which is 1.2 plus 1.5, the whole of it into cube of the maximum diameter. And the envelope surface area will be calculated by using the formula pi times A, which is 1.2 plus 7.5 into the square of the maximum diameter. These two formulae can be kept with you on a notebook, or you can take a picture of this particular slide. Among the various materials which Sohan discussed yesterday, we have shortlisted metallized polymer, which has got a 30 GSM, 30 grams per square meter weight density, or 0.03 kg per cubic meter. Actually, it should be kg per meter square, I think.
Yes, sir, that is a typo.
It should be kg per meter square. So it's kg per meter square. Okay, so we will work on it. Now again, don't ask us why have you chosen this material. We have already discussed a lot based on availability, based on our past experience. You are welcome to use any material that you think is suitable. For the envelope, there are other things like the fin weight, the weight of the gondola, the weight of the avionics, the weight of the payload, and the weight of the ballast, apart from the envelope. So we are going to have a look at the numbers for all of these, and I would request you to do the calculations with me as I go ahead. So the first thing is, and again, I am just showing you the envelope design parameters. We are assuming some values constant. For example, we assume that we are working in standard conditions where the air density is 1.2 kg per cubic meter. This number will change from place to place, depending on the location where you are flying, depending on the season at which you are flying. You have to put the correct value of rho air. And if you want to be very particular, you need to correct it for things like temperature, humidity, etc. But for purposes of the demonstration today, we are taking density as 1.2. The lifting glass density also varies as the function of the atmospheric conditions, but we are going to assume that to be 0.2 kg per cubic meter. Okay, I'll just start my video also. The fabric that we have chosen is 0.03 kg per square meter, as I mentioned, and the acceleration due to gravity, which is approximated as 10 in some cases, but we will like to work with the value of 9.81 meter per second square. If you have any queries or any doubts, simply ask them in the Q&A session, and I will request Sohan to start answering them because I cannot see the screen other than the presentation. So I'll keep going ahead with it. So now we did some calculations and we found that the mass of the gondola, fin, avionics, payload, and ballast, the total comes to around 550 grams or 0.55 kilograms. And if you convert, so that means, and we want to provide a heaviness of 0.02 kg. That is a number that we want to provide. Okay, this is something that we desire. So in this particular list, the weight of payload and the ballast has been already prefixed. We have assumed the payload to be 0.05 kg, a small camera, and ballast to be again 0.05 kg. But the weight of the fin, avionics, and gondola has actually been obtained after doing the sizing as explained by Sohan. If you want to convert this into forces to get newtons, just multiply by 9.81. So the numbers are shown in the screen. Okay. So here also, I think again, there is a small typo here.
Sir, heaviness should be 0.2 newtons.
Yeah, that's what I'm just trying to correct it. Yeah. So sorry about these minor typos. They do happen once in a while. Okay, let's go ahead then. So we have looked at the design requirements. We have looked at the section of the profile. We have decided the material, and we have also done some envelope, some component weight estimation based on whatever components were available. Now this process is a cyclic process actually. So this is only the first stage. So this is the initial calculation, and now we need to find out a suitable envelope size for our assumptions. So notice that the net lift is going to be equal to the weight of the items minus the heaviness, because we want some particular heaviness. So therefore, we need to have this formula. So we are going to compute surface area and volume, and then using that, we will compute the envelope weight and the aerostatic lift. So let us look at the envelope weight and volume calculation. Remember that the value of the parameter A is 1.2, and the density of the envelope fabric is taken as 30 grams per square meters or 0.03 GSM. Now, to do this process, we need to start with a guess. The maximum diameter is given to us. The maximum diameter has been given as 1 meter. So we are starting with the initial guess of 0.5 meter. Okay, so now with 0.5 meter as maximum diameter as the first assumption, let us calculate the volume of the envelope. So using A as 1.2 and D max as 0.5, can you please calculate the value of this parameter? And please let me know the answer in the Q&A session, in the Q&A section. And when answers are being there, Sohan, can you please read out some answers?
Yes, sir. Sparsh has responded 2.43.
2.43. So Sparsh A is 1.2 and D max is 0.5. So do you really get?
Neeraj has replied 1.22. Satvik has replied 0.3.
Yeah, that seems reasonable.
Santosh 2.44. Sujana 0.3. Srinidhi 0.3. Anirudh 0.3.
I think a lot of people are answering 0.3, and that is what I also got. The answer we got is 0.31 square meters. Okay. Then the net lift is going to be volume into the difference in the density of the gases. Okay. Can you first calculate the volume of the envelope with the diameter as 0.5 using the formula which I had shared with you? Please.
There are no responses yet. Maybe you could mention the values for rho A and rho LTA.
Yeah, I mean, see, rho A and rho N are known, isn't it? They are rho A is 1.2 and rho LTA is 0.2. So it's 3 newtons. How do you get surface area? Pi times A is 1.2 and D is 0.5. Can you get the value of surface area in square meters? And please give me at least 2 digits beyond decimal point.
Sir, there is a query by Jaspreet Singh. He mentions that webcast on YouTube is not coming through.
Okay. Let me just check that. Give me a minute. I don't know why it is happening. So, okay.
It's coming, sir, perfectly.
Yeah, why are people giving us wrong information? Sorry. It is coming. There is a different link. It's not the same link. There is a different link.
I have shared the link on the chats if anybody wants to have a.
But I don't know why somebody wants to watch on YouTube, because we are allowing people to come on the webinar. Okay, so what is the surface area? Anybody has calculated?
Yes, so people have answered 2.8, 2.82, and mostly 2. Yeah, 2.8.
Okay, 2.8. Then the envelope weight will be equal to the surface area into the density into G. That means 2.8 into 0.03 into 9.81. Please tell me the value.
8.24 is one answer. Yeah, 0.8, 0.83.
Yeah, so 0.8 is the correct answer. Okay, so which means the envelope weight is 0.8 newtons. Okay, and the net lift is 3 newtons. So let's look at how we can get the total weight. So if you add up the numbers, so the total weight of the airship will be the component weight plus envelope weight. Okay, how much will that be? 5.4 newtons is the total weight plus 6.2 newtons, right? So that is the weight of the total airship. So now we look at whether the net lift is matching W dash minus H. If not, then we have to update. So this is called as the heaviness condition check. So the net lift for 3 newtons, W dash was 6.2 newtons, and H we want as 0.2 newtons. So what is the value of W dash minus H? It is 6 newtons. And we see that the net lift is half of the required value of 6 newtons. So therefore, what do we conclude? We conclude that this diameter that we have taken 0.5 is not enough. We need a larger size envelope because we were not able to get net lift equal to the self weight minus the heaviness. So what you do is you increase the diameter. And to increase the diameter, we are going to go back now and we are going to use something called a delta D. And that delta D is taken arbitrarily as 0.2 meters. So we are going to increase the diameter from 0.5 meters to 0.7 meters. Okay, other things remaining same. So now the maximum diameter is 0.7 meters. Again, calculate the volume. Can I have the answer, please?
So 0.83 is the answer, 0.84.
Okay, so 0.84 is correct. Moving ahead, again, volume is 0.84, LA is 1.2, L is 0.2, and G is 9.81. What will the net lift? Wherever you see a red question mark, you can expect that I am waiting for an answer.
5.37.
0.37 newtons.
5.37, 8.24, 8.21, 8.2.
Yeah, it will be 8.2 newtons. Okay. Surface area of the envelope, 5 times 1.2 plus 7.5 into 0.7 square. How much is that?
Five point five, 5.52.
So 5.5 square meters is the correct answer. Yeah, you could get it slightly more or less, that's fine. So the envelope weight is going to be the surface area, which is 5.5 into rho fab, which is 0.03, and into G 9.81. How much is that in newtons?
One 1.62, 1.625, 1.61.
Okay, so let's take it as 1.6. So now let us calculate again. 5.4 is the weight of the total system. Envelope weight is now 1.6 newtons. So what is the total component weight? What is the total weight of the airship then? It's very simple.
7.
7 newtons. 5.4 plus 1.6. So let us again check. We have net lift 8.2, weight 7 newtons, and the heaviness required is 0.2. So what is the value of W dash minus H?
Point 8.
0.8.
6.8.
6.8. So what we observe is that the net lift of 8.2 newtons is more than the W dash minus H, which is 6.8. So what do we conclude? We began with the envelope volume of 0.5, a max dia. Sorry, we began with the envelope with the maximum dia 0.5. We found that we are short. Then we increased it arbitrarily to 0.7. Now we are finding that the net lift is more than the required value. So therefore, we need a smaller sized envelope. And hence, we must decrease the diameter. 0.5 was not enough. 0.7 is much more than enough. Okay. So again, we go back. This time I have taken delta D as 0.1 meters. Okay. So therefore, the envelope is 0.6 plus 0.1, and that is 0.5 plus 0.1, and that is 0.6. Just ignore this typo. Okay. So once again, please calculate the volume of the envelope. A is 1.2 and D max is now 0.6.
0.53.
0.53 cubic meters. Going ahead, let's calculate the net lift, which is volume, that is 0.53 into rho A 1.2 minus rho LTA 0.2 into 9.81. How much will that be?
5.2 newtons.
5.2. Okay. Surface area 5 times 1.2 plus 7.5 into the diameter square, which is 0.6 square.
4.05.
4 square meters, let us take. Envelope weight would be surface area, that is 4 into 0.03 into 9.81. How much in newtons?
.2.
1.2 newtons. So going back to our old calculations, the total components are 5.4 except the envelope, and the envelope is 1.2. So therefore, what is going to be the total weight of the airship now? Is going to be 5.4 plus 1.2, that is 6.6 newtons. Back to our procedure. So now Ln is 5.2 newtons, W dash is 6.6 newtons, and H we want as 0.2 newtons. So what is the value of W dash minus H? .4. This value is, so the lift is 5.2 newtons is less than 6.4, which means, what does it mean? Net lift is lower. Do we need smaller or larger? Hello, I would like people to answer, please. Why are people answering on the chat window? I think they have to answer on the Q&A.
Larger. People are replying larger.
Yeah, so the envelope has to be larger, not smaller. So therefore, we are going to increase the diameter. So we go back. Now we increase it by 0.5 from 0.6. So make it 0.65. Can you calculate the volume, please? Looks like people have got tired of calculations.
1.44. People are responding on the chat as well. 0.67.
Yeah, so I would request people do not use chat window for responding. Please use only the Q&A window for responding. I think I have been repeating this instruction since the beginning of this session, and I would request people to follow it. There is a reason behind it. See, the chat window is used by us internally for some communication and also to inform you something. Do not use the chat window, please. Use only the Q&A window. Don't make me disable the chat for all the participants. That will not be a nice thing to do. What about the net lift? 0.67 into 1.2 minus 1 times 9.81.
6.57, 6.58.
Okay, let's say 6.6. Surface area again, pi into 1.2 plus 1.5 into 0.65 square.
0.76.
4.76, we have taken 4.7. Envelope weight, surface area 4.7 into envelope density 0.03 into 9.81 to get the answer in newtons.
0.22. 1 point. 1 point.
Okay, 1.4. Yeah, it should be nearly 1.4. Okay, so the total weight is going to be the component weight of 5.4 newtons plus envelope weight of 1.4 newtons, which becomes, how much is it?
6.8.
6.8 newtons. So now, no need to do any calculations. Ln is 6.6, W is 6.8, and heaviness is 0.2. So what is the value of W dash minus H? It is 6.6. And that is exactly matching with the net lift required. So therefore, 0.65 meter is the correct size of the envelope. Now, all of you must have realized that this process, what we have gone through, is a very painful process because you have to keep iterating this manually. So I don't think this is the correct way of doing the things. What we should do is to make some kind of a program or a code or a spreadsheet through which we can do this method iteratively. Otherwise, it will become a nightmare to do it manually. So the output is 0.65 meters, but we should not keep doing it manually. I think we should go into some kind of a automation. So for that, so this is the final output. We are using a modified GNVR shape for this particular workshop. We have found that the maximum diameter of 0.65 meters matches the requirement of heaviness of 0.02 newtons for a payload of 0.05 with a ballast of 0.05 and to meet the requirements mentioned. Okay, and then if you add all the items, they come now to 0.55 kg. So this is the 3D model of the outputted the calculations. The next thing to be done is metal design, but at this stage I would like to take a short break, and for the short break I would like to actually, you know, launch a small poll so that we can. Okay, give me the next one. Okay. All right, so I'm launching a poll now. Okay. I hope you can see the poll. Can somebody confirm, please? Is the poll visible?
Yes, it is visible.
Visible, right? Great. Yeah, so please answer the poll. Okay, so I have now disabled the chat window for attendees. Those of you who answer the questions in the poll can take a short break. And those who are not answering the poll can take a longer break.
Sir, there is a query by Vaidehi Bishane. It's mentioned that I'm unable to see the poll.
Okay. I don't know what I can do about it because generally the poll is visible to all the participants. I have not selectively launched the poll.
I think it's perhaps because if you even accidentally press submit, then the poll won't be visible.
Yeah, but you can actually resubmit. I think you can take part again. Maybe. Anyway, let's just wait. So around 70% of the people have taken part in the poll so far, and we will wait for some time. Before we go to the next session, we'll just wait for a few minutes. So students, participants who have already answered the poll or who are not answering the poll can take a short break. We will resume in a few minutes. Around 36 people have not taken part in the poll. I wonder why. If they are attending this workshop and if they are interested in what we are doing, I think they should take part in the poll. Don't worry, there is no negative marking. Even if you get some answers wrong, it doesn't matter. So we will resume in exactly 3 minutes from now. The last session is going to be a very useful one because we are going to showcase a spreadsheet that can be used for doing the sizing of an airship, and then that spreadsheet is going to be available to you after the workshop is over. Oh, in fact, we need to talk about petal generation. Okay, sorry. So we are going to talk about petal generation. So I'm going to end the poll now in exactly 1 minute. 85% people have participated, which is good enough for us. So we are going to stop the poll in exactly 1 minute, and then after I complete, I'll hand over to Soham. Okay, so the poll is now being stopped. You can look at the results of the poll. So the first one is, which of the following relations need to be satisfied for airship design? The correct choice is that the net aerostatic lift Ln should be equal to the total weight, excluding the LTA gas, plus the heaviness. And I'm very surprised that only 20 people out of 139 have got it right. The next question was, what is the next step in designing an airship after the design requirements are finalized? It was basically envelope sizing, which is what I just covered with all of you. Which of the parameters remain constant throughout the envelope sizing procedure? Yes, density of lifting and gas and air, yes, it remains constant. The sizing parameter does not remain constant. The sizing parameter continuously changes because we increase or decrease the volume. And hence the envelope weight also will not remain same. It will also keep changing as the sizing parameter changes. So choice number 2 and 3 are wrong. The avionics weight estimate does not change. It remains constant. The next question is, if an airship has a volume of 1 cubic meter, the density of air and helium is 1.2 cubic meters and 1 2 meters respectively, what would be the gross aerostatic lift of the airship? The gross lift is going to be simply the envelope volume into G in newtons. So that will be 10 newtons. Okay. This is gross, not net. So therefore, it is going to be 10 newtons. Okay. The poll is over. And now I'm going to continue very quickly and show you the remaining part of my presentation, which is about the petal design. So now we have to fabricate the airship envelope using petals, right? So if this is the envelope cross section, then if you take a section at the center at any location, and if you look from this direction, you will see that the cross section is a circle because this is the axisymmetric body. And there could be, from the nose, you can actually draw these lines along the length of the airship. Okay, so they are called as the petals. So to construct the 3-dimensional envelope using a flat 2-dimensional piece of material or fabric, we have to go for what is called as the development of a 3D body, and the long strips along the length which are joined together to make this envelope are called as petals. So we are going to look at now how the geometry of the petal can be generated. So at any point, if the radius of the envelope is capital R, then the circumference is 2 pi r. And this 2 pi r, if you divide it by the number of petals, NP, you will get the width of the petal at any point. So this example shows an envelope with the 6 petals. So therefore, each petal subtends an angle of 360 upon 60, that is 60 degrees. So the A to B is the curved part of the petal, which goes from the nose to the tail. And when you join 6 such petals, you will get the envelope. So the question is, how do you generate the profile? How do you generate the profile of the petal? So at any distance x from the nose of the envelope, there is going to be a cross section of diameter capital D and radius capital R. And the length of the petal is going to be on the curved path L, as shown in the figure. So if you want to generate the petal, what you have to do is just focus on this. So the petal is going to have its dimension as 2 pi r divided by np, where np is number of petals at any point. And how do you get this information? L. So if you have some length x1 along the cross section, you calculate R1 using the equation of the curve of the petal of the airship, sorry. You will get the length L1, which is an approximation, because you can notice that the actual shape is curved, whereas this is a straight line. Then at any point x2, you again calculate and get the length L2. And you keep on doing this till you reach the length of the airship. So L1, L2, L3, etc., 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 till you do the length, you will get the total length L of the petal. Okay. Obviously, if you want to have very accurate shape, you will have to do something so that the triangular portion is roughly matching with the curved portion. And that is only possible if you take a small step size. So if the value of x1 and x2 are very small, you will definitely need more calculations, but you will get a more accurate measure and a more accurate geometry. So we will show this to you in the spreadsheet in more detail. I just wanted to give you a basic picture right now. So you will see a spreadsheet like this, where you will see different kind of color schemes used for different types of parameters, and you will see how you can generate the cross section. Okay, so I would like to hand over now to Sohan for the next part, but we can definitely take some questions at this stage. So if there are some questions.
So there is one question from Shravan. He is not clear about the concept of petal.
Okay. So, all right. So now, basically, a petal is the development of the 3-dimensional shape into a 2-dimensional surface. Okay. That is what a petal is. Just give me a minute. Okay. So petal is basically, so what do I say? So if you want to make a 3-dimensional surface using a 2-dimensional sheet of material, you need to create these petals, and we have shown you just now how the petals are created. Now, Sunil Kumar wants to know, are there any alternate methods for petal generation? So I am not aware of any other method of generating the petal. What I've told you is the straightforward and the simplest method. I am not really aware of any other method for generating the petal. But I think when Sohan explains it, probably it will become more clear. Or do you want me to go through this once again? I think, Sohan, when you explain the spreadsheet, would you be able to explain this in more detail, or should I go back and explain?
I'll be able to explain this.
Okay. There are some other questions also. So how do we join the petals to form a perfect figure? First, we join the petals by using some technique of joining, which could be adhesive, which could be heat sealing, which could be other ways, which we will discuss tomorrow. Tomorrow's session is going to be on manufacturing and flight testing. Today's session is on the design and the tutorial. And tomorrow also we will do a tutorial on other things. So Neeraj Mandlekar has a very good question. Should we also consider the joint with respect to overlap layer? Yes, definitely. Definitely we have to keep an allowance for overlapping. That will be explained to you when we show you a video regarding the fabrication. Okay. Shiva Chanupati has answered a question saying that parabolic helium balloon is made by cutting multiple metallic coated long sheets. Basically, they are petals only. They are not anything different. So I think, Sohan, you can start off now. You have exactly 1 hour available to you.
Okay. So let me share my screen. Okay. So this is the spreadsheet that we will be sharing with you. So this would be shared under the general public use license (GPL). So you are allowed to make any changes and even upload them. But at the thing is that anything that you derive from this has to be free of cost. So that's the condition under which we are sharing this. So let's look at the spreadsheet. And this is basically what you are doing. So let me maybe do a split screen, so that way I can also show you what was done earlier. Let me do a screen. So I am guessing that you are able to see both my Excel sheet and the spreadsheet. Excel sheet and the PowerPoint presentation.
Yes, yes.
Yeah. All right. So the first thing that we did in the during the tutorial was we fixed it at the D max was fixed at 0.5. So that's what we have done here. And we get all the parameters that are obtained. Like for example, volume is 0.31. So we get it more accurately here, 0.305. Surface area being 2.8. And like all the parameters, like even the difference between ln minus w dash plus h, which is nothing but your heaviness condition. So we just converted it in a way that LHS and RHS are on the same side. So you just compare it with respect to 0 that way. So in this session, what we will do is we'll learn how to make such a spreadsheet. So what I'm going to do right now is first let me explain to you, these are just the inputs. So these are the in the Excel sheet here, you have the Dmax here. This is the fineness ratio, which is nothing but the length of the airship to the maximum diameter of the airship, that ratio. And these are from the component estimation. This is the requirement that we set, that it should have a heaviness mass of 20 grams. And then these are some of the constants. Rest, everything that you see here is kind of calculated. So what I'm going to do is, I'm just going to delete everything. Okay, for your convenience, what I've also done is I've put the formulas on the side. So we can just write it as we go. So this kind of spreadsheet you can make for any kind of envelope profile, provided you know how to calculate the volume and the surface area. All right. Okay, so let's look at airship length. Now, length, as I mentioned, it's nothing but the fineness ratio into the maximum diameter. So this would be nothing but L. So let me do first one thing for simplicity. What I'm going to do is I'm going to name this cell Dmax. I've already done that. So I just go to this cell name and type D and enter. So that way this cell is named D now. Okay. So whenever I say D, it is basically Dmax. The reason I'm not putting this as Dmax is because Excel uses it as a different formula. There is another function which is basically named like Dmax. So that's the reason. And I'm going to use A more frequently. So that's why I put A here. So just write A there. So any cell that you want to name, for example, fineness ratio. For example, I have not named this. It says D6, column D, row 6. So if I just type FR over here, the name gets changed. So I'm just naming the variables in some sense. Okay. So here, let's come to the first thing, that is the airship length. So this would be equal to fineness ratio, that is 4.25, this cell, multiplied by 0.5. So, or D max. So I just write D here. Okay, so it shows up here that I've declared it and enter. So this would be the length if your D max is this. Now volume is pi over 4a plus 1.5 into D max cubed. So that would be equal to, so for pi, I'm going to take simply 3.14. There is a function for pi on Excel, but let's not get into that. So that multiplied by a, so a I have already defined, divided by 4, okay, plus 1.5 into d. So d is already defined, so d cubed. Okay, so it's 0.305. Let's just check with our old calculations. That's right. And yes, it turns out to be right. 0.31. Same thing, let's do for surface area. So equal to 3.14 multiplied by A and plus 7.5 multiplied by D squared. Okay, so you have 2.817 for, let's just be sure, and it is 2.8. Okay, so we have done that. Now envelope mass is nothing but surface area multiplied by the fabric density, which is 0.03. Remember, this is the mass, not the weight. So that's why it is just, there is no gravity here. So this would be equal to surface area multiplied by G. And so this is your envelope mass. Structure mass is nothing but everything that we had estimated earlier. So all these components except for the heaviness. So all these components added up together would be the total structure mass. So equal to, that would be gondola mass plus fin mass plus avionics mass plus the payload mass and the ballast mass. Okay, so that is 0.55. So the total mass of the airship without lifting gas is nothing but this plus this. It's just the total mass, sum of this. Okay, there seems to be a problem here. So I think I have, yes, this is the mistake. It should be D22, that is surface area multiplied by row fabric. Yeah, 0. So you see that the envelope mass is just 85 grams for 0.5 meters of maximum diameter. The envelope mass is just 85 grams. So this here would be the total mass of the airship without lifting gas. So this is nothing but envelope mass plus the structural mass. This is W dash, total weight of the airship without lifting gas. So that's the product of M dash into gravity. M dash multiplied by G. So let me just have a look at the questions. Yeah, someone just, yeah, someone, thank you for that. Already looked at it. Okay. Okay, so we have had a look at all that. Now lifting capacity is straightforward. So it is nothing but density of air minus the density of helium. So as we know, for your convenience, we have made it 1 kg per meter cube, but because now you're doing it on Excel sheet, you can give more precise values for the densities. Aerostatic lift is nothing but volume, which we have estimated, multiplied by the density of air minus the LTA gas, that is nothing but lifting capacity. So I'm directly going to use that and multiply it by g. That's the acceleration due to gravity. So let's just check. Okay, let's finish this as well. Heaviness. Heaviness is the heaviness mass, that is 0.02 multiplied by gravity. So yeah, there you go. That's your heaviness. And Ln, this is the heaviness condition. So let's equal to Ln minus W dash plus H. So this is that value. What is the maximum payload? So there is a question, what is maximum payload and velocity can be taken by metallized polymer to avoid tear during flight? I think this may be answered by one of the panelists. Okay.
Actually,
So
this number comes from experience, and we have flown small airships of this type even with about 200 grams of payload. But you know, the velocity cannot be too much because at a high velocity, the loads can be quite large, especially the inertial loads. So use metallized polymer mainly for small payloads, I would say below 100 grams. That is what I would recommend.
So just to add to that point, so it depends on also the strength of the material. So if you go for maybe a higher fabric density, so we have considered 30 grams per square meter. So 30 grams per square meter is a very, very light fabric. It's about 30 microns, very, very thin. It may not be able to carry a lot of load and even wind loads. So if you want to go for something outdoors, maybe you can go for higher density metallized polymer. Okay, so let's move ahead with the spreadsheet. So I am guessing that everybody has kind of had an idea as to how this is created. Now, what do we do to get the optimum Dmax? So one way is just do what we discussed in the previous session. Just keep on changing. Maybe earlier we did 0.5, then we did 0.7. We get some value, and then we did 0.6. We get some value. It's not 0. And then we did 0.65, and then we had some value which is close to 0. Now it is not exactly 0, but it is very close to 0. Now fortunately for us, Excel has a function which we can use to obtain a precise value. So what we are going to do is, if you go to the data menu, that's on your menu bar, you will see what if analysis. So under what if analysis, this is under the data tools section. You see an option called goal seek. Okay, goal seek. And what we are going to do is, we are going to set cell, and we are going to select this difference, that is Ln minus W dash plus H. This particular difference, we want this value to be equal to 0. Right? For the sizing to be complete, we want this particular value to be equal to 0, because that is when Ln will be equal to W dash minus H. That is the heaviness condition. So how do we do that? We would want to change this particular value to 0 by changing the Dmax term. Okay, it's pretty much self-explanatory. If you look here, you want to set cell D34. I'll repeat. D34 is this difference, Ln minus W dash plus H. You want to set it to a value that is 0. You want to set this particular cell to 0. And you want to do that by changing the Dmax value, which is this. Okay. And I just click OK. And here, so this is basically 10 to the power minus 4. Okay. It's a very, very small number, and it's very close to 0. Now you see that the status also has updated. It says sizing is complete. The precise value is over here, 0.65081848. Okay, so you can try this. Let's say I start with a very, very arbitrarily random number, 0.1. So we have a huge difference here. So let me repeat that. I go to data, what if analysis, goal seek. I want to set this difference, this particular cell, and I want to set that value to 0. And I want to do that by changing the Dmax cell. And I click OK. You see that the value changed. Okay, that's how you basically size, and you don't have to even know how to program. So you just simply use Excel, this function, to just obtain the size for your sizing parameter. Okay, so let's, any questions on this part? Can multiple cells be selected? No, under goal seek, you can only select one cell. However, if you are interested, you can look at, there are several other options here under what if and a scenario manager and data table. So one of those would have that option. I think that is, if I remember right, it's scenario manager. You can have a look at that. But for our purpose, we only have to change one parameter.
Yeah,
Now,
one more thing I want to add, that when you do goal seek, remember the cell that you are changing, like in this case, it is D5, the Dmax, that cell cannot have an equation. It should only have a number, because Excel cannot play with an equation to change the answer. Okay, so the cell which you are setting for goal seek should not be an equation. It should have a constant entity. The cell that you want to set equal to 0 can have equation, or when you want to set it to some number can have equation, but the cell that is to be varied cannot have anything other than a number. And also one more thing is, sometimes goal seek is not able to get the answer, so it will just keep running in circles, and then you can stop it. And you may like, if you like the answer it suggests, you can say okay. If not, you can get the original thing back. Yeah, please go ahead, sir.
yeah. So if you want to, let's say this is specifically for modified GNVR shape. Now, if you want to make your own spreadsheet, maybe pick your own envelope profile, a different one. So you would need to have a volume equation and the surface area equation. Now, I know it's a bit tricky to get volume equation for something, like if it's just a spline curve, or you just come up with a shape and you don't have it. So for that, what I would suggest is you should revisit your calculus. So by using integration, you would be able to calculate what the volume is. So if you know what the equation of the curve is going to be, you will be able to calculate the volume as well. And that's precisely how we obtain these equations, volume and surface area equations. So you can do it for any given shape. You just need to have these equations for this method to work. Okay. All right. So that is about the sizing, and I'm hoping everybody was able to follow this. So let's go ahead with the next part, which is generating the profile. Now, if you look at this shape, it's already been generated. What I'm going to do is I'm going to delete all this. Okay. So even X, for that matter, I would be removing all of it. So let's say we want to generate 100 points. Now I've done some fancy formatting here for your convenience, so don't worry about that. So it's just going to stay blue here for now. So we automatically get the value from here, which was the optimum size that we designed 0.65. We decide, let's say we want to do 100 points. So the first thing you need to do is you need to divide the length into n number of points. So you need to get the least count. So what I'm doing basically is I'm dividing this length into smaller sections of for n numbers, for n points. So that would just be, each of the least count would be 0.27625 away from the previous one. I hope that makes sense. So let's start generating the, before we do that, let's have a look at the profile again. So we have the elliptical region. for which this is the equation. Here R is the radius. Okay, so this is the radius of this particular region. And then we have the cylindrical region, which is basically a fixed diameter. Okay, fixed radius. So we have the R of X to be fixed here in this particular region. And then we have the circular curve, the arc. So for which this is the equation. And then finally we have the parabolic segment for which this is the equation. So I've put the start and end points here. So it's basically the elliptical region starts from 0 and goes up to 1.25 times the maximum diameter. So you can just calculate that. So it is nothing but 1.25 into the maximum diameter. Okay. Same thing with the cylindrical region. It starts at where the elliptical region ends. So that's why 1.25 to Dmax. And then it goes up to the end, which is 1.25 plus A into Dmax. You can see here. The circular region starts at the end of cylindrical region, and then it ends at this point, which is 1.25 plus A plus 1.625 times Dmax. It turns out to be this value. And the parabolic region is the last bit, which is from basically 1.25 plus A plus 1.625 to the end, which is L, basically the total length of the airship. Okay. So with this, what we are going to do is we are first going to generate points, equidistant points from 0 to L. And we have identified the least count to be this particular number. So if we have 100 points and if we space them with this particular number, we are going to start at 0 and end at 2.7625. So the first value is obviously 0 because that's where we are going to start our profile. And then the next one would be this value, the cell which is previous to it, plus the least count. So which is L over N. Now I'm going to put dollars here, F4. So this is because I want to fix this cell. So when I put dollars in front of D and 20, it's not going to change when I have to drag it down. So this particular cell is fixed. Okay. So as I said, the first point is 0. The next point is 0.27625 away from the previous one. And I just drag down until I have this 100 points. And that's the reason why I have this color formatted. So this is where we have put it. So 2.727625 is the total length of the airship. And we have used 100 points for this. Okay. So the next thing is writing the radius. Now I have formatted this in a way that it is easier for you to understand. So the blue color means it's the elliptical region. So elliptical regions means this is the equation. The purple colored region is basically the cylindrical region. So it's this particular area. And this orangish color is for the circular one and the final green one is for the parabolic one. So it would format it automatically. So now let's write the equation for R of X, so which is this elliptic. So that would be 2 over 5 multiplied by square root of 2.5 into D. Remember, I have made this variable D multiplied by X, which is here in this case the changing cell, X minus again X squared. Okay.
So on you have to type 2.5 instead of 2.4. You made a mistake in the equation while typing. Yeah.
Yeah.
2.5.
Thank you for that. Yeah. So as you can see, it's 0. We drag down until the blue point, which is the elliptical region. Okay. So here you can see the petal, the envelope is being formed, right? So this minus R of X is nothing but negative this. So I just write equal to minus this cell. And I just drag it down and I have the bottom up now. Okay. So let's go ahead. Let's write the equation for the cylindrical region. This is pretty straightforward. It's equal to D max divided by 2. Okay. So it's simply this, and I will drag it down until the end of cylindrical region. So you see it's being extended here. Same deal again with this. Okay, so we have generated the cylindrical portion now.
So,
Now let's
where do you define this capital D that you used? You use capital D in the formula, so you have not explained.
Yes. I have explained it in the beginning. Let me explain it to you again.
So, okay.
So here, so let me first delete this in that case. So if you go to formulas, there is something called as a name manager here. So I've defined this D and it is defined as D5. Now let me delete this for sake. This would actually break a lot of things. See, you can see that a lot of formulas don't work now. So what I do is if I click on this particular D max value, see, it shows D5 because it's column D, row 5. Okay. So what I just do is I just go to this particular area and I rename it as D, just simply D. And there you go. So wherever you want to type a formula, you just have to write D and it shows up here. So if I just say D, it's going to be this value. I hope that answers your question.
Yeah, yeah.
Okay, so let's get back to our profile coordinate generation. So we have generated the cylindrical portion now. Let's go to the circular one. So here is the equation. So that's equal to, that would be square root of 16 into, again, this is the D that we just defined, D squared minus, now X is this, minus 1.25 into D, again, minus A also I have defined earlier, A into D, bracket closed and all of this squared. Okay, seems okay. And minus 3.5 into D. Okay, so I just drag this for the, let me do this together. I'll drag this all the way down to the circular region. Okay, and here you have it, the circular region. Now the last bit is the parabola, for which the equation is here. So that would be equal to square root of 0.137 into D multiplied by, now I don't know if I have defined L. So let me see, I have defined L. Now again, this is L is nothing but the length of the airship. It refers to the cell which has the length. Minus X is your coordinate. And bracket closed. So let's just drag this down. And okay, so the last one, I think I need to drag this a little bit down. So, okay, so there is a bit of an error here. So don't worry, we are almost there. So the next point, what we can do is we just drag this down. We can forcibly make it 0 because it's anyway equal to 0. No, because that's because we have not defined that range. So let's make this 0. And now I think, yeah, now I think we have closed the curve. Okay, so you can have more number of points here. If you have, instead of 100 points, you can do the same thing with maybe 1000 points. You'll get an even finer shape. Okay, let me have a look at the Q&A. Yes, this spreadsheet will be shared under the GPL license, as I mentioned. But you will have to be very careful while using this because I'll show you there is a bug in this. It's not exactly a bug, but let's say I change the fineness ratio. Uh, I'll make it maybe 3.8. You're going to see that error. So that smoothness here is a bit changed. So it's because it's going to be more evident if I make it 3.2 maybe. Yeah, you see this? So you need to do this profile generation every other time you change the value for fineness ratio. So for now, let's just keep it at our value 4.25. Okay, so this part is just the envelope generation. Now, more important is the petal generation part because this is what you would require to make an airship envelope. So there is a question by Sheikh Zishan Ali. Is this kind of spreadsheet used for every envelope shape? Yes and no, because it depends on what you're comfortable with. To be very honest, I don't use a spreadsheet for sizing the airship. I use MATLAB. But this is how I started making airships. This is an easier way and it's more straightforward. Whereas it doesn't allow you to do a lot of things like if you want to do some fancy things like you want to do calculus, but you want to use calculus to get your volume, not use a formula. It will be a little bit tricky to do that on Excel. So, and also you saw that there is this bug whenever I change the fineness ratio, it kind of changes it, right? So that kind of error would happen if you use Excel. However, this is a good point to start. Okay, so this is the place where we are going to generate petals. Uh, so let me explain to you what's happening here. So I think many people had questions earlier, so I'll maybe just revisit what it is. So it's basically like you guys would have played basketball or not exactly football, but basketball. If you look at the basketball, they kind of the shape would be something like it would be spherical, but you see this kind of shapes on them. These are basically 2D structures which were then stitched together, and then basically that's what forms a balloon. So petals are nothing but that. So we want to form envelope. We want to make a 3D envelope, which would take a particular shape when it is inflated. And for doing that, we need to generate petals. So let's look at this particular envelope profile. So let's say we have this shape, okay, and along the x direction, this particular length is going to be projected like this on the petal. Maybe it's better to explain using the spreadsheet. So I'll just move there to explain that. I hope I'm doing good on time, Professor Pant.
Yeah, you're okay on time. You have exactly half an hour.
Okay. So let me just revisit this again. So let's say you look at this cross section. You have this airship. What you would see is you just basically you're cutting this airship. So what you would see is basically a circular cross section. Anywhere you cut, you're going to see a cross section which is circular. Now this gives us the first clue. What we are going to do is, let's say you want to make this shape using 4 petals. So what I'm going to do is I'm going to draw 2 lines. So that way I have 4 arcs. So all these arcs are of the same length along the circumference of the circle. I just cut them and I have four sections now, 4 sectors. So basically if you project them on the airship envelope, so this is the dotted line that you would see. So I'm projecting this point. So I'm basically projecting this point, and that point would be these dotted lines. And this point would be this dotted line. For these two would be on the other side of the airship, which is not visible when you see from one side. Okay. Yeah. So let's go back. Yeah, so what we do is basically, let's say you want to have NP number of petals. It could be, in this case, 1, 2, 3, 4, 5, 6. So let's say NP is 6. So what you do is you divide it. So 360 divided by 6 is 60. So you divide it into these sectors. So you have 60 degree, 60 degree, 60 degree, and 60 degree. Basically forms like a hexagon. Now this red line that you see, it's basically going to be the width of your petal. Okay? Because if you cut it from this point of view, you basically have this curved surface. And if you spread it across, it's basically like this, and you spread it across, it would be the width of the petal. So basically, if you want to get the arc length AB, what you would do is you would divide the circumference of the circle, which is 2 pi r, divided by the total number of petals. So in this case, 6. So 2 pi r divided by 6 would give you the width at petal width at any point. Okay. I hope that is somewhat clear now. So you're basically getting the width of the petal. Same thing, similarly, we have to do it for the length as well, because along the length, so here we are. So let's have a closer look at this red circle. So we have the width, which is 2 pi r over LP, I just described. So if you take this point X, so let's say at this point, the radius is R, and you divide it by NP, 2 pi r, what you get is the width of that individual petal. So this is at this distance L. Now let's look at this distance. How does it translate here? It's not going to be the same length as this X. It's going to be this arc length. Okay. So this arc length is going to be this length in the petal. So it's going to be longer. Okay. So that's the reason why X, you cannot, even if you take X along this envelope, it's not going to match exactly with the petal X points. So that this is going to be your L. Now, how do we get that L? This is how. So we are going to use Pythagoras theorem. So we already divided the along the length into many small points. So we take one section like that. So let's say this is the first segment. What we will do is we obtain the radius at that point. This you can obtain from the envelope equation. And now you estimate what the length is going to be. So that is going to be L1. So you know X1, which is the first one. So there is a question by Shravan, the width of the petal isn't constant throughout the length of the airship. Yes, it is not. You can see it clearly from the second image here. So it's going to be changing everywhere. So because R also changes. If you go back to the equation of this, that R is exactly equal to this. See, R of X, you have these different equations, and obviously for petal also you have that different. Basically, you have different widths along the length. Okay, so yeah, so we take first segment X1, and at that point we see what is the radius, so which is given by the envelope equation. We draw a hypotenuse, which is going to be L1. Let's just name it L1, corresponding to X1 R1. This you can calculate using Pythagoras theorem. Okay, so you have the first point for L1. The second point, what you're going to do is, instead of taking this as the X1, you take the whole length X2. But while calculating for this length L2, you will only take this segment. So basically this part. So this part is nothing but X2 minus X1. Okay, and this length is R2 minus R1. Does that make sense? I hope it does. So basically this would be R2 minus R1, and that's how you get L2. Now at any given point, if you want to find L, you just add L, whatever L value you have to the previous L value. So that's why you have this. I think it would be a little more clearer when you look at the Excel sheet. So let's go back to our Excel sheet now. And this would be the final one in our discussion for today. So let's say we want to make 4 petals. Okay. So you have a circle, you divide it into 4. So we are going to follow somewhat like this. Okay. So this is just, we just copy the value from here, from the profile coordinates, and I put them here. It's just copied, just reference to that particular value. Okay, so the first thing is petal width. Now what is petal width? We already discussed this. It's 2 pi r over np. Okay, so let me just do it maybe. So here I've used 2 pi, a little more precise. So this pi function is for the pi value. So B18, what is B18? It's the radius. So it's this 2 pi r, okay, r of x divided by np. So np is the number of petals. Now notice that I have put dollars here because I'm not going to change this cell value as I go down. Okay, so that is the petal width. So if I just drag this all the way down, I have the formula applied everywhere. Now for element length A, so the first one is simply equal to the starting point x. Now this is where you would want to use a little bit of Pythagoras theorem. So what have I done here? So remember this x1 and r1, this particular thing. So here in this case, how do you get x1? The x1 value is nothing but so if this point is 0 and this point is x1, the value can be written as x1 minus x0, right? This width is nothing but this point minus this point along the x direction. So that's what I have done. A19, let me maybe rewrite it. So equal to square root of, so this is basically obtaining the distance hypotenuse. Okay, L1. We are obtaining L1. So that would be square root of this particular equation, xi plus 1 minus xi squared plus ri plus 1 minus ri squared, square root. Okay, so that element length, basically we are calculating L1, L2 that way. So square root of, so this is x1, okay, xi plus 1 or x1. Maybe I should put brackets here because I'm going to square them, minus x0. Okay, so this would be squared plus this value. Okay, again brackets because I want to square them, minus the previous Rx squared. Okay, and I close the bracket for square root, and this is going to be my L1. Okay, now I just apply this formula everywhere. I'm hoping it's correct. Yep, it looks like so. So just copy paste everywhere. Okay, so now we have all these L1, L2, L3 up to the L100 because we have 100 points. We obtain all of that. Okay, so next X petal. So this is nothing but the element length because you want to map this into a 2D surface. Okay, so you see that for every L, you have to go on adding X1, X2, sorry, L1, L2, L3, so forth. So what you're going to do is the X direction. The first one obviously is going to be the first equation, the first point of your profile. The second one, however, would be the previous value, that is 0, plus the element length that you just calculated. Okay, so let me just do that. Equal to this value. So this is the previous value, that is Li, plus this distance. Okay, that distance is this. There you go. Okay, so I just drag it down all the way. Let's look at Y petal now. Same thing here, Y petal, the first one, Y petal is nothing but the Y coordinate. So I'm not calling it R coordinate because it's not radius anymore, it's going to be width. So that's the reason why I named it Y. So we have the Y coordinate here. So the first one is simply this R of X divided, first one would be petal width divided by 2. 2 because we want to have two segments. So you have the profile like this. So you want to divide the width between the centers. So halfway here, halfway down, halfway up, halfway down. Okay. Maybe I should just delete this. Okay, anyway. So this is just doing that. So it is basically 2 pi r NP. 2 pi r over NP, you have already calculated the width. That you're dividing by 2. So you get the positive coordinates and the negative coordinates. That's the idea. Okay. So it's basically just, let me just repeat that. So you have the petal width divided by 2. And you drag them all the way down. So nothing changes here because that's the formula that was already existing. This is nothing but minus of this petal. Okay. So I'm not going to drag it down. I'm hoping it's a bit clear now. So there you go. This is your petal. The inner one that you see is what this coordinates are representing. Now, someone did mention about seal margin or weld margin. So that is why we have this particular cell. So 0.02, which is 2 centimeters. So we are going to have a margin of 2 centimeters for sealing. And we just keep it here. So what do? We do nothing to the X petal. So X petal is exactly precisely the same as this. You see that the values are not changing, just the same. However, for Y petal, we take this Y petal and add this weld margin. That's about it. So you just offset it every point by 2 centimeters. And that's the reason why we have dollars, because we want to have it fixed. So we just move it all the way down. Sorry, that was a mistake. Just drag it down all the way, and it doesn't change the value because that's the formula that's already there. And there you have the inner petals. Okay, so I want you to have a look at this. So this is just comparing the envelope to the petal. So look at this. The envelope is kind of this shape. It's a bit bluffer. The petal, however, is longer, and it's a bit. It's not as wide as the envelope, and that's a general thumb rule that you follow. You cannot make an envelope with just one petal. You would at least need 2, but although the shape would be very bad. So ideally, for a small airship, you could start with 4. 4 is a good number to start with for small envelopes. So this number particularly is 4 is all right. You can go to 5 or even 6, maybe 8 if it's a very big airship. But yeah, so we considered 4, and this is the petal. This is the coordinate for the petal. Now this is very important for, we will see the actual importance of this tomorrow when we talk about envelope fabrication. What we're going to do is, we are going to take these coordinates, and there is a sheet here which says import file petal margin. So this is the petal coordinates with the margin. So you just take it to a CAD file and you have to make a 2D drawing. So I would recommend using CAD because on Excel, whatever template you get is not going to be true size. So this is just an indicative figure. It's not up to scale. So you have to make a 1:1 scaled PDF file, get it printed, and then that is going to be the template for you to cut your petals, to fabricate your envelope. And that we are going to talk about tomorrow. I guess that concludes the Excel part. Are there any questions?
Sohan, I have a question.
Yes.
Will you be able to show 6 petals and 8 petals in the same spreadsheet?
Yes.
Will they get plotted automatically? Let's have a look.
Oh, they wouldn't be plotted one on top of the other. It would get replaced. So let me.
Let us just see what happens if you make 8.
So let me make 8. It just gets thinner.
Yeah.
So compared to the envelope, it becomes thinner. So if I say make it 2, so it's going to be a bit bigger. It's not going to be.
Yeah. So let's keep it at 6.
Yeah.
Okay.
So it's possible. There's a question. Are we supposed to use only GNVR shape for regatta? No.
No,
There
not
is.
at all.
Yeah.
Not
So
at all.
there is another spreadsheet that I have gotten the permission to share with you guys. So that's based on Gertler shape, series 58. There's another one that is very popular among people who go for regatta. That's because it has a lot of, you can actually change the shape very well. So that I think if Johannes Ising would be joining tomorrow, he may be able to talk about it. He also has a spreadsheet, but that's for Gertler. Although the sizing methodology is a slightly different one, you have to fix the volume in that case. But you are, to answer your question very briefly, yes, you can. You can use any profile you want. Is this whole process done from scratch when an airship is designed, or sometimes old values are taken into consideration? Well, it depends. In this case, it so happened that the requirements were very similar to what I had encountered in my PhD study. So the structural weight was all same. So what I did was basically for my PhD, I had a 6-petal airship envelope, same size, same. Basically, everything was same. The fineness ratio, everything. Although the gondola was different, the motors were different. The envelope was same. So we do recycle these envelopes depending on whether you can do it or not. And you don't have to remake this Excel file again and again. So this is particularly for a modified GNVR shape. So if you want to make something which is on modified GNVR airship shape, you can use this spreadsheet without having the need to create a new one.
So may I just give a suggestion? Since the students, the participants here may be new to airship fabrication, there is no harm if they use only this shape for the regatta. Okay, there is no problem. While there is no restriction that you have to use only this shape, you are welcome to use any value of A. We have used A 1.2, you can change it. And also, if you want to have some other shape, like the NPL shape or any other shape, you can make a similar spreadsheet. There are no marks, there are no special points for shaping it. It should perform well. So it's up to you.
So, okay, there is one question which I think I should address. Did we consider petal weights in the previous equation for the weight of the airship? Yes, we did. Actually, the petal is nothing but the envelope weight. So if you cut the petals into, if you cut the envelope into 6 parts, so let me maybe very briefly show you the airship from another slide. So if you look at this, are you able to see my screen?
Yeah, we can see your screen.
So so if you look at this airship, this is the one that I had made for my PhD. So you see that red lines. So those red lines are nothing but where the petals are sealed. Okay. So petals are nothing but what is needed for making the envelope. So it's just stitched in a way that when you inflate it, it forms that shape. So that's the reason. However, to add more to your question, whether have we considered the weld margin? No, we have not considered the weld margin in the envelope weight. So there is a very easy hack for that. What I noticed is usually it takes about 10% of the envelope weight. You can maybe add more as well, but typically 10% works. So what you would do is, so in this envelope mass, you have this equation, which is nothing but surface area into the density of the fabric. You just multiply it by 1.1. The answer will change. So if I do Goldsik again, it is going to be slightly bigger than the what we got, which is 0.65. So if I do this 0 by changing this, it's going to be maybe 0.66. Yeah. So see, if you consider the petal weld margin, slightly going to be a little bigger. So it's up to you whether you want to consider that or not. In our case, what The reason why we did not consider it is because we actually put a little more weight in all of these components.
No, but it's a good idea, I think, to consider. I think it's a good idea to consider.
Yes.
Also remember, the envelope will not just contain of the petals. There will be joints, as Sohan has mentioned. Plus, there will be many patches at some places. You may have to strengthen the envelope at some places, etc. So it's good to take 15 or 10% margin. I'd like to answer a couple of questions which are there. So Vignesh has asked a question about is the volume constant or dimensions constant for regatta? So for the regatta, the rules will be put on the website. So look at the website www.deltas2022.in for all the rules regarding the regatta. We don't want to answer it here because this is just a workshop for designing the airship. It's not necessarily married or tied to the regatta. So check the regatta website for these kind of questions. What may be the probable total cost to build a remotely controlled airship of the size covered in the webinar, Shravan? So now that number depends on whether you already have those motors with you, propellers with you and all that. You know, we really don't have any fixed number right now, but maybe Sohan can give an idea.
So it depends on the hardware that you use. So the motors, everything that we mentioned, it may be even including the radio control. It would come up to around, if you go for the cheapest radio, maybe around 20,000 with the motors and all the avionics. Plus the material is not very expensive. Material could be one roll you would get for 2,000 rupees. Helium is where you would have to spend a little more money. So that would be about, if you go for a smaller cylinder, maybe 10,000. So approximately 30,000 would be what you would need to do one flight. This is considering helium.
Yeah, so we will talk tomorrow about helium versus hydrogen. And also remember, now Sohan mentioned about a remote control. Now, I don't think you should buy a remote control only for this airship. You should either try to buy a controller which can be operated by a mobile phone. You know, you can use an Arduino or some other controller which can be managed, which can be controlled by a Wi-Fi based telephone, a handheld mobile phone. So there are many options available for you to cut down the costs. Okay, so this number is not readily available with us because, as Sohan rightly mentioned, it's a function of many things. Right. Let's go ahead. Are there any more questions? We are just 5 minutes away from the close of session today. So there are just 5 minutes remaining. So we can use the last 5 minutes for answering any questions or queries that you may have. So the floor is open for any questions or any queries. If there are no more questions, then we would like to stop for today and then resume tomorrow at 6:30 p.m.
Sorry, sir. So I could share the Excel file over Zoom now. I can share a link from where they can download.
That will be great. So you can on the chat window you can do that.
Yes. So yeah, this is I just uploaded it on the drive, so people may just copy it. Let me know if it works because.
So it says view only, Sohan.
Yes, they would be able to download it. I don't want people to edit it because then the source file would change. Is download happening? Just let me know.
It says view only and it says request edit access and you will get hundreds of emails requesting you.
Okay. So let me just.
And before we go, I do have a poll for the third session, which I'd like to launch as soon as possible. So Sohan, I think you hold on to this. Let us do it tomorrow, not today.
Okay.
Let us share the spreadsheet tomorrow. Today, I would like to launch the poll. I would like to launch the poll for the third section. Okay. Can 3D printing be used to make petals? Is it feasible? Vedant, we are using petals which are flat envelope sheets. Okay, so I don't think you can use 3D printing for that. Okay, I'm going to now launch the third and the final poll for today, which only has 4 questions. and it will just check how much you have been able to understand about what we have covered today. So the poll is online, my friends. Please answer the poll before you go. There are many people who are leaving without answering the poll. So it's nice that nearly 78% of people have participated so far in the poll, and I'll be happy if almost everyone does, and then I can share the results and close the session. So I'm going to give you another maybe couple of minutes. We are sorry, we cannot give you much more time because it's already 9:30. But couple of minutes more are available for you to answer the poll. One more minute remaining. 90% people have answered among the people who are present. I think only around 9 people are remaining. So please quickly answer so that we can discuss the correct answers also with you. Okay, I'm going to stop the poll now. 93% people have participated. The poll has ended and the results are being shared with you. So which function of Excel was used by Sohan today to obtain the exact value of the airship sizing parameter? The answer is gold seek, which roughly half the people in the audience have got correct. Others are answering, the wrong answer. Question number 2 is about the airship having a volume of 1 cubic meter. If the density of helium is 1.2 and 0.2 air and helium, what would be the net aerostatic lift? The net lift would be 1.2 minus 0.2, that is 1 into 1 plus into 10. So that would be 10 newtons, which many people have answered. Then, is the envelope length larger than the length of each petal? The answer is no, petal length is more. And that is the correct answer given by 50 people. But other people are still confused. 43 people think that the envelope length is more than the petal. No, how can it be? Envelope length is always going to be less than the petal. In fact, Sohan has even shown the figure. Okay. What can be done to increase the accuracy of the envelope? The correct answers are use large number of petals, which more than half the people have answered, and also to reduce the width of the petals. If you increase the petal width, you are going to get less accurate shape. And if you use less number of petals, you are going to get less accurate shape. Okay. So I would stop sharing the answers. And thank you so much for being present today. There is one question. So Suman Ghosh says, would we be receiving certificate after tomorrow's session? Suman, the certificate will not be given tomorrow. They will be given later after we look at the results of the poll, and we also look at how many people are present in all the sessions. So tomorrow it will not happen because we don't have the time for it. It won't happen tomorrow. It will happen later. Okay. With that, I think if there are no more questions, I would like to thank Sohan for explaining the things so nicely, especially for repeating the petal generation, which I had tried to explain. Perhaps I went a little bit fast. So thank you so much for explaining it once again with a nice sketching.